Welcome back to part 11 of Password Cracking 101+1. At the end of the last video, we conducted a fingerprint attack on a Kerberos hash that we would typically get after a Kerberoasting attack. This fingerprint attack was created by extracting the clear text planes from our pot file, so all of the previously cracked passwords we had, taking the last field of that pot file, which is our clear text passwords, running expander over it, which, as we found out last time, expands and mutates the candidates it's given. We then uniqued the output and created a word list from it. That word list is then used in combinator mode with itself to make some really weird and wonderful candidates, and we were able to use that to crack our Kerberos hash. We're moving on now to prints. Prints is a fantastic tool, I can't rate this enough. This is a candidate generator. Another one of these things that I feel is a little bit more unknown than it should be. It's been around for a long time. Jens, the author of Hashcat, who goes by Atom, created this a while ago. And what this does is this builds chains of words for us. So we give it a single dictionary, and then we say to prints, we want passwords that are a minimum length of 8, or we want passwords that have 2 elements in them, or 4 elements in them, or a range. It's quite flexible. The example here is taken from the GitHub itself, so you can go there and have a read. But to try and make this a little bit clearer, if we were to tell Prince to guess just 4 character candidates from our dictionary, let's say we gave it RockU, Prince would go through the RockU dictionary and generate 4 character candidates in the variety or in the combinations shown here, because these are the only ways that we can generate a 4 character password, as you can see, for everything from a single 4-letter password, or a 4 character password I should say, to 4 individual elements for 1 character passwords. So 4 isn't probably a valid use case for us, because we would probably look to brute force and exhaust key space within the 4 character range. But you can see how prints can be very quickly used to generate really quite crazy candidates. It's very similar to a kind of like a combinator attack, but it's different in that in a combinator attack you could create a combinator attack using 2 dictionaries that are identical, therefore potentially doubling up on candidates, whereas assuming you've got a clean word list that's already unique, Prince won't be able to do that because it would be selecting 2 or more different elements from a single word list. So close, but not quite the same. Nonetheless, though, very, very powerful, and Prince is one of my first go-to things after the usual kind of dictionaries and rules are exhausted. So how do we conduct a Prince attack? First of all, as I mentioned in the last slide, make sure your dictionaries are clean. Do dedupe them first. We don't want to be wasting precious compute cycles on running dupes. But a Prince attack would be as shown below. You run Prince, give it a dictionary, a good dictionary, a fairly good sized dictionary, so it's got a lot to work with, like RockU. We'd set a minimum password length of 8. 8 being, for reasons just described, we've probably exhausted the key space of 7 and below, but of course this could be adjusted. We then pipe that straight into Hashcat, and then it's business as usual. Prince will go through and start creating 8+ character passwords based on multiple elements from your RockU dictionary in this case. And you can extend that further by saying I want to have a minimum and a maximum element count. You can do that by looking at the Prince help screen, and it can give you the appropriate switches. Jeremy Gosney took that one step further a while ago and thought, why not take the output of Prince, which is already pretty good, and feed that back into Prince, because, why not? So you can see here, we're piping that back into Prince and then back out again into Hashcat. And it created really weird and wonderful candidates that you certainly wouldn't get in a million years with traditional attacks. So you never know, this might be something you want to look at just to sort of see. These attacks generally are running for quite a while. They're more sort of, we're moving now towards sort of being designed for closer to infinite runtime now, if not infinite runtime itself, which means these attacks probably won't end, depending on the parameters you set, of course. But yeah, so this is a case of, go for it and see, and then maybe after a day, a couple of days, or hours, however long you've got, cancel it, and you could try something else. In this example, we've also introduced the -G switch in Hashcat, which is Hashcat's self-generated rules. So up until now, we've always looked at passing Hashcat rule files. Hashcat has the ability to generate its own random rules as well. Now, the algorithms used in that are not actually 100% sure on. But needless to say, if Hashcat's self-generating these rules and it's just deciding what to do each time randomly, then we're now moving towards sort of non-deterministic output. So we don't have complete control over our command anymore because Hashcat's doing some of the thinking for us. But it's absolutely awesome to see it go, and some of the candidates it creates are absolutely fantastic. You generally sort of see people running this anywhere between the kind of 100 and 500,000 rule range, depending on what you do. Of course, is up to you. But yeah, it's really good to sort of give this a go and see how it works for you. There is a delimiter request open on Prince that has been open for quite some time. By delimiters, we mean, of course, putting spaces or a comma or a colon, or basically something to separate our elements, a delimiting character, because Prince doesn't support this. There's no real indication that it will do. However, recently there has been a comment on that GitHub by Royce Williams, who goes by Tycho Tifnus. He's another part of Team Hashcat, and he said there is a new combinator out called Combinator X, which has not been long released, and it does have the ability to sort of do this with a few little caveats, but that might be something you want to look into. Okay, rule debugging. So rule debugging allows us to understand which rules are effective, which in turn gives us a bit of a deeper insight into really how people are choosing their passwords, because we can see that, you know, the majority of people in a given data breach or in a given hash set all like to use 123 exclamation mark, or all like to, you know, capitalize the first and last letters, or whatever it might be. Now, this blog here is one I wrote for a former employer, and it's the one I wrote when I created one rule to rule them all. So it goes through the steps and kind of what I did. But the hashcat command that I ran each time is shown here. Now, when I was doing this, I was going through several different rule sets to gauge performance and efficiency, and when I did, I would substitute, of course, the rule name here for the name of this debug stats file. But apart from that, this command kind of remained the same throughout. But importantly, when I wanted to look for which rules were performing well, we needed to enable debug mode in Hashcat. And debug mode 1 will just give us the finding rule. The finding rule being the rule that augmented our candidate in order for us to crack the hash. I wasn't really interested in the original word, so to sort of save time and space, I was just trying to just look for the finding rule. And you can see how these have been sorted afterwards, after a run. In this particular case, you can see we've uniqued and reverse sorted this to get a count of the number of rules. 68,000 times we had a colon, which is don't augment, just leave the vanilla candidate. And then you can see here $1 added a 1 to the end. Toggle the character at position 0, for example, and you can see what are sort of popular and common trends in terms of password augmentation that will allow us to really get a good idea of how people choose their passwords. So this was the command run. We always save our output to a debug file, so we can actually do some work on this afterwards. And very importantly, we disable our pot file in each and every run. The reason being, every time we run Hashcat, anything we crack goes to the pot file, which means Hashcat could then look inside the pot file in subsequent attacks to see if we've already got a match, because there's no point in Hashcat going to work cracking something that we've already cracked previously. So we want to disable the pot file, which means don't save anything to the pot file, and therefore Hashcat has no frame of reference to just really look to see if we've cracked anything at the start of each session. So every time Hashcat saw RockU with a different rule against the same hash list, it was effectively seeing it for the first time. Okay, so we had very sort of reliable statistics there. Okay, that moves us on to the next exercise, a Prince attack. So we're going to crack the hash here at exercise 11. It's an NTLM, so I'm not going to go and cat that out first. We all know what an NTLM looks like by now. Use a rule and crack the hash. What was the successful rule? Okay, so let's get into Kali here, and I'm going to go straight to the command first, and let's paste this in and step through what we're doing. Okay, on your Kali VMs, you will have the Prince processor folder inside Hashcat, and pp64bin is the binary here that we're going to use. So we're going to take Prince processor, and we are going to run it across the Google wordlist.txt in our wordlists folder. We're going to set a minimum password length of 8. I appreciate we haven't exhausted the 7 and below character key space, but this is generally sort of good practice with Prince, because you would have done if this was sort of done in the field. that's going to generate some really cool candidates, and that's going to then pipe those candidates to hashcat. We've got an NTLM hash, which is mode 1000. Here's our hash pasted. We're going to run one rule to rule them all over the top of it, and very importantly, we're going to enable debugging mode and create a file that we're just going to call debugging. So hashcat's going to run through that, and it's going to crack it instantly in 0 seconds. You can see we got an attack in standard in mode because we were piping data into hashcat. And then we can also see the clear text password here. So it looks like it's the word describe, but with brackets kind of breaking up half of it. Now, we have got a file called debugging, and that file has stored the finding rules. This was our debugging mode number 1, debugging mode value 1, I should say, and we can see we've got this this rule. So what did that rule actually do? We did touch on in a much earlier video how rules are created and what they do, but we can have a quick look here to see what's going on. The first part of this rule we have, there we are, is caret bracket, which is going to be around here somewhere. Okay, so prepend character X to the front. So what this looks like is it's going to prepend an opening bracket to the front of our password, which would be correct based on what we've just seen here. Prepend a bracket to the front of our password. The second part, O5 close bracket. So if we look further down, ONX, this is the one, override. So override character at position N with X. And we can see here, override the character at position 5 with a close bracket. If we jump back up here, starting at position 0, 1, 2, 3, 4, 5, we can see that's been the case. Override the character at position 5 with a close bracket. So pretty weird and specific rules there. I didn't deliberately edit one rule to rule them all to make that work. That there is a rule inside one rule to rule them all that has that, so that wasn't a fictitious rule. But clearly, I've picked a rule that would have worked in the context of allowing it to crack quickly for this training session. But that gives a really good insight into how people are choosing their passwords, and across a large data set, really encourage you to enable debugging, to actually have a look. So if you've got really, a big sort of like millions and millions of hashes to run over, then it can be really quite insightful to see what's going on there. Okay, so there we have it. We've now had a look at debugging rules, so we can identify what rules are working and what rules are working the most efficiently. Thanks so much, and look forward to seeing you in the next video.